So my name is Pranjal Upadhyay and I'm IIC MVLSI student currently in my second semester. Previously, I had uploaded a video on YouTube on my channel where I'd actually briefly described what I learned in my first semester. As a continuation of that series, I am making this video series where I'll try to very quickly summarize whatever I studied, subject-wise and chapter-wise wherever applicable, and let us see how far I can go through with this. The purpose of this, the purpose of making this video series is basically just so that I can first of all myself revise the things that I've studied and who can actually watch it is that if anyone is curious as of what this subject was about, specifically if like you are curious as of what is taught in this subject in INSC or is the gist of things that we tend to learn if you have scored a great rank in GATE and you have cleared a VLSI interview, then and if you're just curious about what is up in this course, then you can probably watch this video series. But I'm not claiming to be a teacher or a professor of any sort. It is just something that I'm doing for myself to revise. But if you just want to get a gist of things, you are more than welcome. But if you find if anything that I'm describing is erroneous, feel free to comment or correct me wherever applicable. That out of the way, I will also update the description with whatever material I refer to. For example, I'll attach the playlist that I watched so that I could strengthen my AVLSI basics. And what this AVLSI basically is analog VLSI. So I think without further ado, we should start. This AVLSI had I'll basically just cover the theory portion for time being. That what was the theory that is expected of you by the time you pass in this AVLSI course. There were theory assignments and lab assignments, but I don't think so I'll have the time to go through them. If I'll have, I'll certainly go through them. And there are different reference books that can be used for this course, but I personally like this book because it basically follows and aligns with much of the content in this course. And first in chapters are what basically you had to do in this course of Razavi CMOS analog circuits, and I'll use that sequence flow. So in a way, this video series is also Razavi's Razavi book summary also. You can kind of say that it's a Razavi book summary. I am just going on the theoretical aspects, and I don't really think that I'll have the time to like go and discuss every example or questions at the back. But maybe I'll pick up one or two if time permits, or depends upon the enthusiasm I feel for continuing this video series. So now, without any further ado, I'll just start off, and in this video clip, I'll try to just summarize chapter 2. So let's get started. Now, chapter 1 is basically just about intro that why analog circuit design is still relevant, and also I won't elaborate on these kind of things. So again, I'll only elaborate on technical things wherever applicable. On too basic or too easy things, I won't spend much time on that because I personally already know that. And if you're watching this video, you also probably already know that, assuming that you have cleared your gate exam and you are in a good position, or maybe even if you're in BTech, I'm assuming that you have studied these subjects and thus you have now considered to watch this video. Great. Now that out of the way, let us just start. So this chapter I have divided into these many chunks. That first chunk is structure and symbol. Then we'll go to IV characteristics. Then we can go to second order effects. Then we can go to MOS device models. And then finally, the final comments for this chapter. Great. So structure and symbol, I don't really think that I need to elaborate since we are just revising. So it is already known to us this guy is all about. Let us directly go to IV characteristics. And the first segment here is the VTH. Now we already know that the expression for VTH happens to be this guy where phi ms is the metal work function minus the semiconductor work function. 2 phi f or phi f here is Fermi potential, Q deb is the depletion charge, and Q is C ox is the oxide capacitance. And this can further be elaborated as this particular expression that you can see here, where the gamma is body effect coefficient. So do I do I recommend rote memorizing it? Not really, but you should have just search some kind of intuition that specifically for NMOS, if you increase VSB, your VTH will increase. From this, other intuitions also should be able to draw. That is, for example, if your what will be your effect on VTH for all these various parameters. Let's try to logically think what will happen. So I'll just consider the case of VTH is increasing. So when will VTH increase? And opposite will happen when these parameter opposite thing will happen to these parameters. Let us start in baby steps. So N sub, or basically it is the doping concentration of your substrate. So clearly, if the substrate doping concentration is more, that means that the gate has to put more effort into basically repelling that dopant charge to actually be able to invert the channel. So yes, VTH will increase if N sub will increase. What about the length? Greater the length, greater the basically the length across which the inversion charge has to be established. So from that, we can kind of intuitively comment that if I'm increasing my length, my VTH will increase. This also implies that if I'm scaling down my device, which is basically the agenda in VLSI to scale down our devices, VTH is low. VTH will decrease, which is necessarily not a good thing. Why? Because lowering the VTH also increases the leakage and other complications come in the way, which we will discuss further down the lane. W, there is not so far there is not that of a strong dependence on W in whatever I studied, but definitely you can search through it. One exercise that you can do is actually try to plot VTH versus W on any simulated tool like KDIS, but I don't think so there's a direct way to do that. So you can do that as a homework exercise yourself if you're that much curious. Now, what about VDS? So for short channels, there's one effect called drain-induced barrier lowering, if you recall. So yes, so if we increase our VDS, VTH will decrease because now the gate starts to lose the control and drain starts to dominate and invert the channel. So this means that if VTH is increasing, this guy should probably decrease. If T aux is decreasing, then VTH will again decrease because again the electric field strength will increase. So less we can invert channel by applying lesser threshold by applying lesser gate voltage, or alternatively the threshold voltage will decrease, which implies that VTH will increase for increase in oxide thickness. And what about temperature? The simplest intuition that we can actually build here is the that we know that in semiconductor there's this valence band and there is this conduction band. We know that thermally electrons can excite and jump over here, and alternatively a hole gets created here and electron is available in conduction band. This implies that this process is actually amplified, or it gets more and more as temperature increases, right? So this means that this basically means that if I'm increasing the temperature, thermally generated carriers will increase. And so this implies that if I increase my temperature, my VTH, what would happen to my VTH? Can you infer what will happen to my VTH in that case? So I'll give it to you as a thought exercise. Although we are revising, but if you are watching, I'll give it to you as a thought exercise, and we'll get back to that. Now, let us go to derivation of the square law current, which we all have already seen, but I'll just quickly go through it. So the basic idea is that you're just saying that the inversion charge, basically, that you're saying, and we're defining it as a charge per length. We are saying that this inversion charge in the channel is basically equals to C ox, where this is per area, and this times W, which means this Q inversion is basically charge along per length of the channel times VGS minus VT minus Vx, where Vx is by because of the lateral field existing in the channel because of the VDS which you are applying. I think that I don't really need to draw a diagram for this. It is quite self-obvious. And now when we try to solve this further, what we say is that since MOSFET is a drift device, that is current flows by mechanism of drift, we can just say that the current here, or I drain here, is equals to Q inversion times velocity. Why this basically works out, because this is a dimension of charge per length and it is in dimension of length per time. So it is basically current only. And now you can just replace this guy with mu E, and you can further replace this guy with minus mu d Vx by dx, right? Because E is the lateral field, lateral electric field, because of which drift is happening to begin with, right? And now when you rearrange the terms and integrate, you obtain the expression of I triode. And when you substitute the saturation condition expression, which is basically VGS minus VT, or which is also called V overdrive, being equal to VT sat, you obtain your saturation current, right? But this is the square law, and we should always keep in mind that this square law is good for hand calculation and your intuition building, but this is not the absolute model. The actual model on which our simulators like cadence work are way more complex. And so, yeah, that is something that we must be aware of. Let's move further down the lane, and now let's go to the region of operation. So we know that MOSFET can operate in saturation and triode or deep triode. And deep triode, we can just say that, let us say deep triode is the condition in which VDS is lesser than twice the overdrive voltage. We already know that triode condition is true when VDS falls below overdrive voltage. Yeah. Cool. And cutoff is, we clearly know it happens when VGS minus VT or your drives less than zero. But now that we are more well informed, we should appreciate that it is actually in subthreshold regime. Right. So this is a basic graph that I've drawn, and this line basically is for VGS minus VT, where Y is this and x-axis is this. So now we can clearly see that for region less than this, here we are having cutoff or subthreshold, right? So I'll just call it subthreshold. Or for avoid confusion, I'll just mark it as C to denote cutoff. Now you can clearly, if your mass is recent, which I know it is, you can clearly see that this region represents when VDS is more than VGS, right? Basically VGS minus VT. So this region corresponds to saturation, right? So this region corresponds to saturation, and this region then corresponds to triode region. Why? Because your VDS is less than VGS minus VT. Cool. So if these things are clear and sub-threshold regime operation is clear to us, but still now in all the things that we covered so far, this sub-threshold is kind of new to us in MTech specifically. Then I'll just write the equation for I sub-threshold, which happens to be good. Again, this is a prox relation. So let's write it anyways. It is VGS minus VT by N phi T 1 minus A minus VDS by phi T, where phi T is thermal voltage, N is ideality factor, and yeah, that's how it goes. Now it is of exponential in nature, and why is this current actually flowing to begin with? Is because even when the channel is not strongly inverted, the electrons or whatever the inversion carrier is, depending on whether it is NMOS or PMOS, they never essentially lose their thermal energy. So as far as I know, I believe this is a manifestation of the thermal energy that carriers possess, that this substitute conduction happens. Also, another thing is that this is basically weak inversion operation, right? Because if you recall, when you are studying a MOS capacitor, when this is the guy is gate, this guy is oxide, and we are basically inverting the channel. So first it gets weakly inverted and then it gets strongly inverted when you say that yeah, channel is formed. But when it gets weakly inverted, which is basically the condition of VGS being less than VT, carriers are still kind of present here. So it is weakly inverted, right? So that is another reason, and this is another reason. So yeah, that was something about sub-threshold region of operation. And that now that we have actually discussed it, I'd say that it is quite an order that we now discuss about GM, because GM is the most important to us in circuit design. And we already know what GM is. GM is basically transconductance, and we typically define it as ID by the control, a partial derivative with respect to the control voltage, which typically is VGS. Now, you know that for saturation regime, GM has various variants that you can write. For NMOS specifically, if I write it is this guy, I can also write it like 2 ID by V overdrive. I can also write it like under root 2 mu n Cox W by L ID, right? So this is for saturation regime. Triode, it doesn't make really sense to discuss GM, but okay, for sake of completeness, we'll discuss it anyway. That for triode, you can just say that GM is equals to mu n Cox W by L VDS. So we are seeing that GM is showing dependence on VDS. And typically, if you just like see a MOS structure, we generally take output from this guy or we take output from this guy. Like regardless, you can get an idea that if my this transconductance, which basically decides my gain, right? Like my gain basically in my circuit is proportional to GM, and if this GM depends upon VDS, this is something that we won't want, like right, that our output is basically affecting our GM. But this is not the precise reasoning that why we don't use triode region for our for our usage. There is a much deeper reason to this, that is specifically that amplifier action is best achieved when the transistor is acting as an ideal current source. But we'll keep that discussion for later. And yes, so this is the basically the triode transconductance. Now, for final region for subthreshold, right? For subthreshold, the GM happens to be equal to ID by N phi t. Now, what I really want that we just keep in mind is that for fixed ID, if our ID is fixed, I'll take a darker pen maybe, that for fixed ID, yeah, okay, so it is not doing me any good, but anyways, for fixed ID, we know that, and I hope we know that typically we will drive for our design processes is around 200 milli to 300 millivolt, and we already know that phi t is of the order of 25 millivolt, and if it can be typically 1 2, and even if you take it 2, we can understand that in this GM expression the denominator here is way larger than that of some threshold. What trying to imply is that for fixed ID, if my ID is fixed, GM saturation is lesser, way lesser than GM of subthreshold. Then when I said that, yeah, GM is very important, it decides the gain. So why do we typically operate transition saturation not in subthreshold in most of our design in these kind of courses? That is again something that maybe I'll address in when I revise the high frequency playlist which I have attached in the description. Maybe when I'll revise that, maybe I'll then elaborate on that. But nonetheless, this was something that I just wanted to again highlight. Okay, so great. And now again, here I just sketched some curves, and this one curve is something that I would want to pay attention to. That is Gm by W by L when I is fixed. What equation is governing the curve of such kind of scenario? We already wrote that Gm in saturation for I being fixed can be written as what? It can be written as mu n Cox twice ID W by L, and we are basically increasing WL, and ID is fixed. Great. So intuitively speaking, if we just look at this equation blindly, we'll say that yeah, it is following some under root relation, so it will kind of grow like that, right? It will just kind of grow like a under root model. But is that will it go infinitely? Because this means that when W by L tends to infinity, my gain will GM will also tend to infinity. Is that correct? No. That is not correct. So what we need to understand here is that we are fundamentally ignoring the fact that when my I is fixed and I'm increasing my W by L, some term we know that I depends on W by L. So if one of the dependencies is increasing, some other dependency must decrease. And that here happens to be V overdrive, right? If you imagine the current equation, if I'm increasing W by L for constant ID, V overdrive will decrease. If your drive is decreasing, we must recall that this GM curve which we are sketching is specifically for saturation region. But we know that if the overdrive keeps on decreasing, eventually the transistor will transition into sub-threshold regime, right? So that means that if I'm plotting my GM with respect to W by L, eventually it will, yeah, it will increase, but a time will come when it will transcend to sub-threshold regime, right? When it transitions sub-threshold regime, so we know that ID is fixed for sub-threshold, as we said in the problem statement, and the GM now is basically constant, and I think we can already imagine that because ID is fixed, phi t is fixed, n is fixed. So basically, this GM will saturate, right? So it won't just keep on increasing. So that is something that I wanted to just highlight. So we just not simply follow the given equation blindly, but we must think a bit deeply that what can happen if I change one parameter, because everything is so much interconnected here. Okay, so that was one thing that I wanted to like highlight. So yeah. So this being said, now, let us just talk about second order effects. Now, a question comes to mind is that what I mean by first order effect, second order effect, third order effect, like what is the definition? And in my experience, I could not really find a clear-cut definition to distinguish the two. But what you can basically understand is what I have basically understood is that first order model is basically the ideal square law model, right? In talking when talking of MOSFETs. So ideal square law, where we are basically ignoring short channel effects. In second order effects, we basically talk about short channel effects, to be honest, as far as I've seen, where we are basically considering that when you further scale down the device too much, what kind of changes happen in your ideal square law model. In your third order model, we basically add on other things like effect of traps perhaps, or such kind of things which can like negatively affect, not negatively, but which basically affect your MOSFET model. And there can be higher order effects, depends upon it basically depends upon the actual current modeling equation or model by which our simulators work, but let us not go into that kind of depth. Okay, so now body effect, what is basically body effect? Body effect basically means that if you are basically applying a certain bias on your body, right? Or it's better to be said that if you are basically changing this voltage between source to body, a threshold voltage will change. And as we said before, VSB, on increasing this guy for NMOS, VTH will increase, right? But what is the intuitive explanation of that? Intuitive explanation of that can be the intuitive explanation of a body effect can be this, that if you are having this MOS structure, right? And you have your N, you have your N here, you have your P here, and you have your gate. Okay. So if this guy is source, this guy is drain, this guy is body, so typically we know that we keep these guys reverse bias, right? Which implies that here some, I'm assuming the channel has not formed yet, so some depletion region is over all around here, right? Some depletion region is here. Because I'm sorry, because we have kept this device, these junctions basically reverse biased, and so some certain amount of depletion region is all over here. Right? So now the thing is that before inversion sets in, we know that the charge on this gate must mirror the charge on this guy, right? And I know that if I increase my VSB, that is, if I increase the reverse bias across these junctions, my depletion width will increase, which implies that my depletion charge here will further increase, right? If my depletion charge further increases, what will happen is that now I need even more charge over here so that the charge here and here equates, and then after that, inversion starts to happen. This means that wider the depletion region here, the more harder it is for the gate to invert the channel. So that is the basic intuitive explanation that VSB, as VSB increases, which means that depletion width increases, which implies that inversion depletion charge is increasing. So this basically increases your VDH. That is the intuitive explanation behind that, and equations are already out there to model such kind of a behavior. Great. Another is short channel effects that we basically take into account, considering the fact that our L is small. Channel length modulation, we already know that in the channel, there is some depletion region contributed by the source, some depletion region contributed by the drain. And if I say that this depletion region is del or L dash, here there is L dash. So what basically happens is that the effective channel length decreases. And because of that, we see the manifestation of finite output resistance in the transistor characteristics and the ideal square law model current in saturation regime is multiplied by this guy, right? Which is basically equals to del L by L, which comes from binomial expansion when you substitute L minus del L in the ideal diode current equation in a square law regime. So yeah, that is quite clear to us. And then subthreshold conduction also we have already talked about what this guy is all about. There are certain implications also of subthreshold conduction that we can kind of discuss very quickly. So the what are some of the implications of subthreshold conduction? We define a term called subthreshold slope. SS, I'm writing it as, and we just say that it is 1 by log ID by VGS. And the idea and the agenda in industry currently is that we want to decrease subthreshold slope. Why? So that the off current decreases. In some of the, it's not always the agenda, but yes, we want to basically decrease off current. Why? Because we already described that this sub-threshold current, it is basically dependent on VGS minus VT, exponential of VGS minus VT by M phi t, and also on 1 minus E minus VDS by AT, right? It is basically proportional to that. So we know that as the technology scales down, VDH is decreasing, which means that this guy is increasing, right? So that is the basic idea. So that being clear to us, basically the main problems of threshold slope is just that off current is increasing. But yes, there is a course that I'm currently pursuing also in this semester, which is neuromorphic analog VLSI, quite kind of a niche course where basically we'll try to design circuits in subthreshold regime. So that's something interesting. Now, velocity saturation is just that we know that in a MOS characteristic, which kind of look like this, output characteristic to be specific, what happens is that at a certain high VDS, what happens is that electric field can become so high that the mobility saturates, because we know that mobility saturates at very high electric fields, and if VDS is of that kind of value, mobility will saturate, as a result of which current will prematurely saturate, and then we see that rather than following this path, current will just saturate here, say, and yeah. So where can this happen the most? We know that electric field is what? It is voltage by length of the channel. Speaking in a very approximate brute terms, and I'm only talking about magnitude. So if I'm decreasing my L for a fixed VDS, electric field will increase. And so the tendency of velocity saturation, of mobility saturating will increase. So that is one of the reasons that velocity saturation happens, specifically in short channels. Great. Now, why is subthreshold conduction also a problem in shorter devices? That also I already discussed, because shorter the device, we have to scale down the technology. Shorter device also means lesser threshold voltage, which again increases the subthreshold current exponentially. So I think we already discussed that. Now, drain-induced barrier lowering basically implies, I think, which we already discussed at the start, is that it is the loss of gate control, that if you're increasing VDS, your threshold voltage is decreasing. Yeah, great. So let us talk about the final topic, which is punch through. The punch through, what is basically punch through is that when the depletion regions of source and drain basically merge, so they form a conductive path. And now a lot of current can flow, which is basically very much damaging to the device. And basically it just forms a conductive path even when the gate is off or when the gate is not active. So about this guy, I don't know much in detail, but this is basically you can basically understand that this high that the drain and source depletion will extend to this great extent only when VDS is high. So you can basically expect that in this curve that I'm drawing for output characteristics of MOSFET, it will kind of go like this, like huge current is flowing, and this will basically burn off the device, right? If I have drawn in quite small of a window, I'll just draw it again. So what I am trying to say is that if this is the output characteristic of MOSFET, then at high enough VDS, when basically the J source and drain depletions merge, a lot of high current, basically I'm showing the directional electron flow, can just go from here to there, and high current will flow, and this will basically burn the device or damage the device, as far as I know. But if I'm like, again, as I said in the start, if there's anything you find faulty with this discussion, please correct me, you and I'm just open for more discussion. Great. So let us go to the MOS device model. So this is how the layout looks at the top. We already are familiar with this guy, but this is how this guy looks at the top. This black portion is called contact, basically the metal contact by which you are basically injecting the current to the device. And this is how it looks from top. This guy is gate. Okay. And you will basically memorize this guy the moment you start doing layouts on Cadence, and yeah, it will be a fun experience. Now, why do we need multiple contacts in this transistor layout? Like I could have I could have gotten away with a single contact. Why I'm using multiple contacts? It's just to increase current density and reliability. Like you can understand that if either one, if I'm placing just one contact on this source and drain terminal, so you can understand that if it gets damaged, it is making my device less reliable. That's one weak reasoning, but another reasoning is just to increase current density. Like, for example, if I'm pumping some current from here and see, like, I'll just draw this guy like this, okay? And here is my contact here, here's my contact here. So you can intuitively understand that if I'm pumping current from here, the resistive path will decrease for multiple contacts, right? And if I have just single contact, the resistance will be more. So that is the basic idea that we want to decrease this contact resistance. So that's also one of the ideas that we are using multiple contacts on layout. There are other reasonings too, which you are free to explore. Now, let us go to the capacitances in a single MOSFET and how they arise. So I'll just quickly go through how they arise. So one capacitance that you can always observe is from this gate to your body. You can see a capacitor, literal capacitor being formed, right? Like this one plate and this here whole guy can be another plate. Another capacitor that can form is this overlap capacitance, right? That this N guy and this guy are overlapping. Similarly, one overlap capacitance can form here. And if you want to give them formal names, what can that be? This guy from gate to body is CGB, then gate to drain overlap CGD, gate to source overlap if the source is drain. So this is the CGS, it is a CGD, right? I'll just highlight it for now. This is the CGS, this is the CGD, this is the CGB, and this is the drain to body. So that is basically this guy, this metal, this drain guy is also like trying to form a capacitance. This guy also form a capacitance. And we are not going into the basic physics or a detailed physics discussion of why these capacitance are there and or like what and why of the physics involved, but we should appreciate this that for high frequency analysis, these capacitances are what basically limit our bandwidth, right? Because you know the high frequencies, these capacitors will essentially try to short or basically form short paths here, 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 here. So that can disturb our biasing and many other, not biasing because it is in DC, but it will disturb the high frequency behavior of our device, right? So that is one thing that we need to keep in our mind. One more thing is that here, COX, that you'll also study in your DVLSI, but this is a basic fact that you can kind of keep in your mind is that when channel is not inverted, COX is spread evenly throughout the channel from drain to source. When channel is in triode, we say that the COX is basically split half between drain source and drain terminals. And when it is in saturation, we already know since pinch off has happened at drain, so we just say that capacitance at that end is zero, and towards the source end, it's 2 by 3 of COX. Okay, so that is one small fact that I found worthy of mentioning. And we typically ignore CGD in all our these models. Why is that so? That is something that for timing leaving for you to think if you're watching. And let's move ahead and just talk quickly about a small signal complete model. So this is how the small signal model looks like. You are already familiar with this in Gate, where you must have you must have had explored this. You have already explored this. You have already also I have drawn the wrong symbol. It is resistor bad, and you have already seen this guy, right? So you have already dealt with this model. You also know this because of which I know that you are having some Miller effect flashbacks. And these are some new guys, but I don't think there is any problem of incorporating this. We understand that yes, these exist, and so in the model, just these kind of modifications can be made. One thing here is that this guy, so this is because of body effect. One more thing now, which begs answer, is that what is basically small scale, right? So it is already available, and already I think we all know that why we are saying it is small, because first of all, mathematically we say that it must satisfy the Taylor series assumption, and next is that the linearity concerns, right? That is similar small enough that it does not disturb the linearity of the circuit. And there is a much more deeper explanation if I try to elaborate on these points, but since it's a revision, so I'm not going into that kind of a detailed depth. And again, now GMB is equals to a derivative of I with respect to here the control voltage being VBS, because we are talking about body effect. This derivative happens to be this guy, and you can just now say that it equals to eta times GM, where eta is of the order of zero point 0.5. So we can now understand that basically GMB is quite less than GM. Right? And often we basically ignore GM in our analysis in circuits, but we'll still try to see in our single stage amplifiers that sometimes GM can decrease the gain, but sometimes GM can also increase the gain and output resistances, as we will eventually encounter. Some final comments are there to be made. That is, what is the performance of NMOS versus PMOS? So NMOS offers higher gain, it has higher speed. Why higher gain? If you write, and I think you already know that this guy is the intrinsic gain of the device. So what is GM dependent on? Mu n. And we know that mobility of n channel device is much, much more than p channel device, right? And the deeper explanation to that is that hole mobility is less and electron mobility is high. Why? Because holes are more tightly bound to the nucleus and all that, but I'm not going to into all those details. But there's a good mathematical and semiconductor physics level explanation to this, but it is already a well-known fact, so I'm not really elaborating on this at the moment. And speed also again is higher for NMOS, just because you can just simply say because of mobility, right? And noise immunity, but we find that for flicker noise specifically, PMOS is better. Now, why is that so? We can discuss that when we discuss noise, but what you can understand here basically is that there are certain trap states, right? I think we already know what trap is here. Trap state is that, say if this is the oxide and this is the semiconductor, there are certain trap states at the interface. What are these trap states? These trap states are basically the silicon dangling bonds. Like if this is a silicon atom, so if it is just at the boundary, like this is just an intuitive explanation, okay? It's not exactly what happens, but again, you can say that this is a dangling bond, right? And here is the oxide. Basically, these interaction of these things cause the formation of traps, and as electrons flow here, because of these traps, some random noises come into picture. The surface because of the surface traps, and that's called flicker noise. And what happens to be the case that since we know that flicker noise is proportional to traps, for NMOS, the channel is just like at the interface close to the oxide. But for PMOS, the channel is a kind of buried. That is, channel is kind of not exactly adjacent to the interface, and so the trap states are lesser for PMOS. Okay, as trap states are lesser due to buried channel. So yes, PMOS performs a bit better on flicker noise. Not bit, it performs better on flicker noise. Now considering when to consider channel as short. Typically, what I have found in my studies is that, for example, if you're working with an 80 minimum channel length nanometer technology, which is your basically your L, if you're working with a twice of L, still you can approximate a long channel, and you can comfortably apply your square law model, which have models which have studied, and they considerably give accurate results. But yes, for minimum technology node, even in fact, what if I'm recalling it correctly, up to 100 nanometer, you can still comfortably ignore short channel effects, or below that, short channel effects like really just shoot up. But again, what is short, what is long is again a very relativistic concern. But these are the typical value ranges. Now, talking about FinFETs and nanosheet, these are some advanced devices which are like, the agenda here is to have a more spatial overlapping or spatial covering of the channel by gates, so that we can have a better spatial electrostatic or electric field control over the carriers in the channel, so that we can have even better performance. There are now, so this was all about chapter 2, and I think there are two unanswered questions that I have left for you as the viewer, if you are still seeing, which is quite incredible that you have seen this far. But two questions that I have basically left is that, how and why? How and why is VTH affected, or V threshold is affected by temperature? And second question, and the second question was that I just wrote below only, that what is happening to my memory? I just wrote it, but I'll just summarize it again. That why do we typically ignore C, not gate to drain, it should be source to drain. Why do we ignore source to drain in our modeling of capacitances of MOSFET? Okay. So source to drain. So I hope you're getting the question. What I'm saying is that in this model, why I'm not including this guy? Like these two terminals also I can place, right, arbitrarily, if I'm just saying here, here, here. But also, I'll just explain it anyways. You can see that here physical capacitors are being formed, but here is a capacitor being formed. So I think you are kind of lost, because even I am kind of lost, to be honest. I'm just a student, so I'll just also try to do some research on this. And yeah, so these two questions are what we are left with at by the end of this discussion. And this was just a summary of the second chapter. Again, thanks for watching, and study hard, study well, and maybe I'll see you in the next video when I talk about discussion about chapter 3, which is basically single stage amplifiers. This was very semiconductor physics based, so that's why it was kind of brutal, but we'll try to introduce more intuition in the third chapter. Razavi has done all the further analysis of circuits from third chapter onwards very rigorously, very mathematically, but we'll try to use intuition wherever possible. We'll try to reduce the burden on our hands and try to just arrive at some intuitive conclusion, so that we can quickly figure out why a particular circuit topology is better than this and in what regard. So again, thanks for watching, and I'll see you in the next one.